Okay, so hello everyone. Welcome back to the eighth section of the series of video tutorial. And last time we were discussing how to come up with a Newton-Raphson nonlinear solver to simulate the nonlinear behavior in some of the active trusses. And previously we've also covered the topics of how to develop the bar element using the central difference and how to assemble the stiffness matrix and the global force vectors. So with that, I would like to move on to a new example section. So to really start learning something new about these package. And in this example, and also in the next example, the primary focus would be on planar mechanism. So mechanical engineers has done this wonderful job of creating a lot of um, great mechanism that we've been using in our daily lives. And more specifically, the one we're going to be focusing on today is this scissor mechanism. So I would like to show you one of it. Let me change the light settings. So these things can deploy, change its configurations, and you typically see it being used in many places. For instance, in the construction site, you would see, let's say, the construction crew members using these mechanisms as a lift. They can bring the workers from construction workers from ground level up into a specific elevation so that they can install the windows or work on the roof, so on and so forth, right? And also, in some of the most commonly seen deployable tents, you see these complaint mechanisms being used to achieve those rapidly deployable tents that we typically use for many events. And today, this example we're going to be working on is going to be relatively straightforward. We are looking at these scissor mechanisms with four bars or four beams, basically for bar systems, and the length of each of these bars, or maybe beam, depending on how you want to call it, it's about square root of 2 meters long. And again, we're going to be using this quite fictitious cross section. Which is with the Young's modulus of about 2 gigapascal, close to any sort of a plastic, and the cross section is just about 1 centimeter by 1 centimeter. And the first thing I would like to discuss here is actually how do we capture the potential bending in these bars or in these linear elements that we have in the system mechanisms. So when the system was loaded, what could happen is this particular element, they are able to actually bend quite a lot if the load is large. So the model we're going to be using is called the pseudo-rigid body model, and it's developed by Professor Larry Howell, a very famous professor at Brigham Young University. So he developed this model and taught these models in his pretty famous textbook, Complaint Mechanisms. I do recommend you to get a copy of that. Pretty cool, and actually I've got one signed by him during a conference, so that's definitely quite amazing. But anyway, so the idea in this pseudo-rigid body model is that we're going to lump some of the deformation to a specific element so that we can greatly simplify the simulation. And for a beam like this, the way we are going to lump it is by introducing additional rotational springs, 3-point rotational springs to represent a beam. And we're going to be doing 3 of them in this particular representation we're going to be doing in this example. So the equation is given here, and let me just briefly give you an overview of how this is developed. Of course, if you're curious, feel free to get a textbook. It's actually covered in great detail in the section 2 and also in the section 3. So for a beam member like this, um, if we apply a pure moment at the both end, what will happen is this particular member is going to bend, and the way it bend is actually going to just create a part of the circle. So this actually will become part of a circle um, with a radius r. And if we recall some of the memories that we've learned in the fundamental mechanics classes, what we realize is that the governing equations for a beam like this, the theta ds, would be related to m naught, which is this moment that we apply to the beam on top of the ei. So I is the second moment of inertia of this beam about the bending direction, and the E would be the Young's modulus. So because the moment diagram in this case is pretty much just a rectangular, right? It's a pure moment-induced bending behavior. We are actually going to be able to simulate and also not simulate to solve this analytically quite easily. And the theta over a length of L. Let's say L is the length of this particular beam. Um, and the result we're going to be able to get is by doing these integration from 0 to the theta naught, the theta, and that really needs to equal, if we move the s to the right-hand side, um, that would be 0 to the length of L, m naught ei, and this is going to give us a ds. So the governing equation for a system like these is going to be m naught L over ei. That's the right-hand side, and the left-hand side would be theta naught on the left. So this is basically what kind of curvature or what kind of rotation we're able to get for a specific beam with the EI constant. And what we hope to do by representing it with multiple springs is we want the springs to be able to give us a rough approximation of the shape by representing these continuous beam with the three springs. And actually, let me keep that, but try to make things a little bit smaller so that I can fit some additional. Oh no, I'm actually just delete it. I think I'm able to allow to delete it for now and just keep the most important equation here. There we are. Move it up. Okay. So for this equivalent system, what we're going to be doing is we're going to have three rotational springs, and our goal is to try to figure out what kind of spring constant that we need so that when we apply the moment there, this thing will give us the same rotation. So for each of the spring, the rotation under a moment m is going to be represented using, let's use another term, phi. And this is another spring. And this is going to rotate another phi. Phi when m naught is applied to it, right? Because we are applying a pure moment bending, every spring sees the exact same rotation. Then when you have three springs, oops, you would generate these three phi angle there. And because of that, when you turn that into a circle, just based on our basic understanding of trigonometry, these theta naught shall equal to 3 phi, right? That's a pretty straightforward calculation. You've turned 3 phi angle, and therefore the total amount of turning for the theta naught would be 3 phi, right? And this is can be represented for K spring, M naught divided by K spring, and therefore, from here we actually obtain this equation, M naught L over EI, and that should equals to M naught over K spring. And if we take out the M naught and reorganize the K spring, oops, I think I'm missing a 3 here. Uh, yep, phi is M naught over K spring, so that's why this is missing. Let's reorganize it a little bit. So K spring shall be 3 times EI over the L, which is the length of that element. So this is how we get this equation. So hope that reminds you of some of the basic mechanics derivation we've been doing in the undergraduate. If you look for more details or you want to derive for some of the other cases, feel free to check out the textbook. It's definitely a great textbook. So with that, we actually figure out what I can do if I want to use these rotational springs to represent this beam. And that's going to be a pretty handy solution because through doing these, we do not need to integrate rotational degrees of freedom into the node. And that actually makes our simulation quite much easier to set up, and it runs so much faster compared to code with it's so much easier to set it up when you compare that with the code that do include those rotational degrees of freedom. All right, so this particular element here, the spring, our 3-point rotational spring, is derived here. So it's called a CD element, central difference element, rotational spring with 3 node. So that's what we have here. So the rest of the code, I think I don't need to spend too much time explaining them. It's basically just setting up the material constants. And I also believe that at this point, setting up the node and the bars is kind of a process that should be quite easy, and you already know that. All right. So with the rotational spring, this set of a code is where we basically derive the rotational stiffness of that 3.3 node rotational spring. And our next job is to set up the assembly. So in this particular assembly, if we go into the assembly class, we'll realize that it does becomes a little bit different from the previous truss assembly we've been using. So it has a node element, it has a bar class, and then it has these rotational spring, 3 node. So 3 node rotational springs we're going to be using to represent the overall bending stiffness of the entire structure. Okay. So going back here to the eighth example, um, we set all these classes, the object we just created, to become part of the assembly, and we're gonna need to design the node, define the node for these systems. So for these, because I want every single bar with 3 holes to have 3 rotational springs in them. Therefore, I actually need to put 5 node per each of these linear bars that we have in the system. So there's going to be 5 node at 1, 2, 3, 4, 5. Let me actually draw that for an easier visualization. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's how I want to discretize this entire beam. So I'm gonna put the rotational spring here. It's gonna give this bending stiffness to represent, give us a way to represent the bending stiffness about these trusses. Okay, for these beam elements. And because of that, there's much more node compared to what we previously have, but I think this is not too crazy, right? So the first 6 node is basically this one, this one, this one, and this one, this one, this one. So the bottom 3 node and the top 3 node, right? And then the next 2 node are the center node there, and the rest of the nodes are just to fill the quarter um, a quarter length of that particular element, linear element there. So after doing that, we would try to plot the entire thing so that we can visually inspect and make sure that all the nodes are at the right location, right? So this is the figure. So indeed, 1, 2, 3, 4, 5, 6, 7, 8, and then another node at the quarter length location of these along this bar element. So everything looks good. So this is something that's pretty nice, right? It's kind of looking quite nice. So we can use these as a way of inspecting whether or not the nodes are at the right location. It seems that everything works. So the next thing would be to set up these bar elements. So we want to connect, say, 1, 9, 7, 9, 7, 14, so on and so forth. So this just keeps going on. Every linear element will truss, not truss, this is technically a beam in the scissor mechanism is represented with 4 bars and 3 more rotational springs. Okay, so this is just how we define the nodal connections for the bars, the areas, and also the Young's modulus vectors for the material property of the bar. And after we initialize it, we can plot the shape of the system, and it looks pretty nice, right? That's what we want. So the next thing is the new thing. This is the 3-point rotational spring. So what does spring give us? We actually have already talked about it a little bit previously, right? Um, it's basically some sort of a rotational stiffness about these particular nodes there. So when there is a rotation, let's say of a phi, and if the spring constant is kspr, then the moment generated here would be kspr times phi. And this is how we relate the moment of the rotational spring and the phi angle. So we'll learn how to define these rotational springs pretty soon in 2 more sections later. But right now, I hope this explanation is going to give you enough information to understand what we are doing. So in order to calculate the phi angle, as you may imagine, we actually need 3 nodes, right? So this is node I, this is node J, which is where the spring is located, and this is node K. So the phi angle would be a function of the location of xi, xj, and then the xk. So pretty much these are all vectors. So by the way, pretty much you can imagine using a cosine function to solve for the angle, right? That seems to be a pretty straightforward way. And actually, that's exactly what we're going to be doing later when we derive these particular elements. But then so far, because these thing is defined using 3 nodes, when we define them, we also need 3 nodes. So I, J, K. So for the first spring here, actually here, the first spring needs to be connecting 1, 9, and 7, right? That's how we want it to connect. And then so following the same pattern, the next spring will be 9, 7, 14, and then 7, 14, 5. It's following that pattern. So as you can see these, if you go back to this figure, I hope this will help you to understand what we've been doing. So after finishing the springs, we're gonna just add another spring to control the deployment angle. So it's basically we're gonna be adding another spring at this location, connecting these two. So that's my 13th spring for the phi angle. And it's doing, let me change another color. It's connecting this red node, this node, and this node. And we want to use that spring as a way of controlling the deployment of my full system. So I want to use that phi angle there to control the deployment. All right, so one, two, three. So this is why when you see here, this is the 13th spring to control the deployment. It's 9, 7, 13. So that's exactly here, 9, 7, 13. And with that, when you actually plot the springs using the plot shape spring number to inspect what you've done, you would see that there's going to be a couple of overlapping springs here. That's perfectly fine. That's actually exactly what we hope to have. Um, we're gonna specify the rotational spring stiffness using the K-spring variable we just calculated, and there's gonna be 13 of them, and that's it. All right, with that, the next new functions our new class we're gonna be learning is these Newton-Raphson folding and solver. So this solver is applied onto the three-node rotational springs, and what it will do is it will allows us to gradually change the designated angle of a specific input. So you can imagine that this red spring here, this number 13 spring here, is a particular motor in the system. So we are connecting it to a electric motor and we are specifying that servo motor to, okay, go to 90-degree rotation angle, go to 12-degree rotational angle, or go to 30-degree rotational angle, right? That's just how things would happen in reality. So we have that ability to do that. So we can tell that the springs to rotate to a specific angle. So this is exactly implemented here. So the input for this particular class would be target rotation, and we change the 13 springs to be a specific angle we want it to be folding towards. So this time it's 0.9 pi. So the springs start with about 0.5 pi, which is about 90 degree. So the rest of the things will be very similar to all the rest of the solvers we've been working with. The support information is here. As you can see, most of them are going to be zeros, or in this pattern of 0, 1, 0. That's basically restricting the deformation in the direction that's perpendicular to the plane. So restricting motion in all the y directions. We want a 2D problem in the XOZ plane, XZ plane. And the number one node is fully restrained. Number three and number two nodes, they cannot move in the Z direction. So that's basically reflecting the roller condition in these two nodes shown here in these example setup that we currently have. All right, and with that, this is actually primarily ready to be implemented, right? We specify the incremental steps, so we want to take it slow and steady. We break that change from 0.5 pi to 0.9 pi into 80 steps, and we allow each step to have a maximum iteration of 30 sub-steps. And with that, let me actually run the result and try to see what kind of oops, it's showing an error. Okay, I have not yet added the class. Do you want to add source code into the selected folder into the path? And this will allow me to run it. All right. So after we're running it, we're gonna have a final result like these. So that's the GIF we generated. Oops, excuse me. I don't want to get into problem. So this is the GIF we generated. That's shown here. So this thing will gradually change this angle from 0.5 pi to 0.9 pi, and that's exactly what allows us to simulate the entire system from this more deployed configuration to the more contracted configuration. So this is basically how we can simulate these this toy I have on my hand in a virtual environment. So this figure here, the plot's deformed shape gives us a way of comparing the final result, the deployed result with what we started, and let's draw in the gray lines. So the final deployed configuration is in these dark lines. So, hope that gives you an idea of what we're able to do with this package to capture the behavior of a scissor mechanism like these. And typically, in the traditional finite element formulation, handling this large geometric nonlinearity is a little bit tricky and a little bit annoying. But with the code like these, we can actually handle it fairly easily. And that's one of the beauty of using these lump parameter models or pseudo-rigid body models, depending on what names you want to call it. Um, it's quite easy to use and give us that ability to capture large deformations. So next time, we're going to still be working with the scissor mechanisms, but we're going to start loading it, and we're going to generate some pretty large, crazy deformation there. So with that, I would like to conclude the section 8, and I look forward to working on the section 9 together with you next time. And with that, thank you very much for your attention, and have a great rest of your day.